All right, everyone. Thanks for coming. My name is Steve Scott. I'm looking forward to diving into the Helios architecture and how we use it to host workloads at data center scale. So it will come as a surprise to absolutely no one in this room that AI is driving the next era of computing. If we look over the last decade, model sizes have increased by around a factor of 100,000. Now it takes hundreds of gigabytes just to hold model weights. Context lengths have grown to 1 million tokens or more, driving large KV caches that have to be held close to the processor. Mixture of expert architectures and stringent latency requirements are causing us to shard models across many, many GPUs that have to communicate together. And then the relentless drive to more and more inference is leading to 24/7 deployments where the cost and energy per token is becoming critical. So this is all causing us to rethink how we design AI systems. Instead of thinking primarily about compute and about single GPUs, we're thinking about compute and memory and network at rack scale and data center scale. We're having to worry about flexibility and resilience. And you can't architect these systems without a deep understanding of the workloads and the data center deployment constraints and issues. And for that, you need customers, leading edge customers that are deploying world-beating AI models at scale. There's no better example of such a customer than Meta, and we've been working really, really closely with Meta on the design of the Helios rack. So I'm going to invite to the stage Josh Held, who we work very closely with. He's the Director of Thermal and Mechanical Platform Engineering at Meta.
Yeah. Thank you, Steve. Appreciate it. All right. Good to see you all today. So thank you, Steve. I appreciate you having me here to talk about Helios, the partnership that we started a while back now, and I want to just get into kind of some general stuff up front and then how we partnered a little bit later. So I think we're all observing the massive build-outs of AI compute capabilities and how that's come with significant challenges across gigawatt hyperscalers like Meta. The data centers that support them, as well as small-scale enterprise data centers. The capital expenditures are quite extreme and demand optimized total cost of ownership at a system level across power, hardware, and software. Cooling and power delivery are first-order design parameters, and of course, performance must follow. Open source frameworks are also important to developing these systems at scale, and AMD has been a big supporter of that, working with us as well. We also have a concept around general performance of CPUs and GPUs working in concert for broad workloads, as well as more customized GPUs for more customized workloads as well. So I'm going to talk some about the major shifts that have gone through industry. One of the major shifts that we've experienced as an industry over the last few years has been the size of scale of domains. Just a few years ago, 8 GPUs was state of the art. Just a few years. Now we've reached an inflection point where we've had to make a shift to rack scale, where 72 GPUs per rack, and with that size domain was needed for cutting-edge workloads. This created the need for a great deal of innovation in several areas. Liquid cooling was one of them. My team, and as well as the AMD team, worked extensively on this. This became a requirement to package these systems at scale. To enable single hop all-to-all topologies, and this represented a real step function in capability, requiring critical innovation from chip to facilities. Compute and memory movement also changed the game for us as well. As flops increased, due to silicon advances, we also had to change how we fed them. High bandwidth was required. Scale-up bandwidth was also another huge element where we had to make sure that all the parts of the system worked in concert in order to feed those beastly GPUs that we had in these very large systems. We had to be able to balance a number of things within these systems in order to make these work efficiently. Compute density also increased fairly dramatically. We're now above around 200 kilowatts of system power for these large systems. And it poses a lot of challenges to our data centers and fleet management and all sorts of aspects. Open standards has also been a really big part of what AMD's done with us. They've pushed Ethernet protocols for scale up and scale out domains, and that's really provided a lot of flexibility to the systems at scale. I want to talk briefly about OCP. OCP has played a pivotal role in not just with the standards it supports, but also setting the tone for interoperability and accelerate improved infrastructure through shared innovation. Helios has been a great example of this, with Meta and AMD architecting Helios together, with open hardware as a cornerstone of our development. It's been a great partnership. Specs for the ORW form factor were made available to all at last year's OCP Global Summit, as well as making automated rack movers and Meta co-design with industry available to all at the OCP Regional Summit in April. What else is on? Okay. Additionally, I think there was a lot of collaboration that occurred between AMD and Meta during this time frame, and the teams really rose to the occasion as using open source as a cornerstone of the development of this entire platform. It was really great to see. Again, fantastic partnership. Oh, hang on. Bottom button. There we go. Sorry, folks, bear with me for a second. Okay. Now let's talk a little bit about the Meta and AMD engagement, what it looked like, the challenges and learnings that we encountered along the way that ultimately shaped Helios. The first one was space, power, and cooling. From the onset, it was pretty clear to us that the high-powered liquid-cooled AMD GPUs at a rack density of 72 would really have different spatial and power constraints. That meant we had to rethink the form factor altogether, so we created ORW to meet the demand of next-generation AI systems. Helios was the first adopter of this form factor. The additional space afforded by a larger rack also meant that we could more elegantly design and power cooling distributions purpose-built for such powerful racks. We also had to consider performance and TCO. In such large, powerful systems, it's really important that is still a cornerstone of what we do, and is identified very early on by the teams that we also had to deliver to a very high standard on perf and TCO with these kind of powerful systems. We also had very tightly coupled design integration. This is where we make all the CPUs, GPUs, and NICs work in concert, not as a collection of parts, but as a combined, unified piece of compute gear, essentially, in order to enable the GPUs to perform at their peak. And lastly, we had to bring this all together, and this is what I call big co-design. One of the biggest challenges of designing these systems is designing them with so many different elements working in concert without local optimization in single areas that could sap performance or actually make the product not as powerful as it could be otherwise. So this took a lot of partnership between AMD and Meta. AMD bringing very deep knowledge of their portfolio, and Meta bringing workload experience, as well as operational experience and deep ties within OCP. I do think during this time, we all learned a lot about building big systems, and I think that will kind of pay it forward for the next systems we'll build together, hopefully. And I do want to take this moment on behalf of Meta to thank AMD for their partnership in this effort. It's been a great collaboration on Helios. And with that, I'll pass the mic to Steve, and he'll talk about the details of Helios. Thank you all very much.
All right, now let's dive into the Helios rack. So you've seen all these highlights before. I don't have to go through them again. The meta point here is that the rack operates as a single GPU, unified shared memory, tying all of the processors together. It ends up having 50% more memory capacity, 20% more memory bandwidth, and 50% more network bandwidth than competing solutions. It's all based on open standards, as Josh just said, tightly integrated and designed for ease of use. So let's look at the rack infrastructure. It's, again, based on the OR wide rack. That wider footprint helps distribute the weight more uniformly, reduces the weight density, gives you more serviceability across the front. It's got integrated management and power in the rack. The power can be either N plus N or 4 to make 3 redundant. It's got a high voltage liquid-cooled bus bar distributing power inside the rack. The cooling is integrated as well. It's got quick disconnects. Over 85% or so of the heat is taken out in the liquid. It also has integrated leak detection. But the star of the show, of course, is the compute complex. There are 6 high-performance switch trays and 18 compute trays, 9 above, 9 below. They're all connected by a set of integrated cable cartridges shown on the right side. On the rear of the rack, they're all individually serviceable. And the cooling and the power and the network connectivity are all blind mate connected. So you just slide in the trays. You don't have to do any cabling in the data center, and it's all set to go. Let's dive a little bit more into the details of the rack. We'll first take a look at the compute blades. So the compute blades are 1 OU. Each one of the compute blades, hey, let's take the heat sinks off there. Each one of the compute blades has a 1P4G node. There's a Venice CPU in the front, has 16 MRDIMMs or RDIMMs, providing about 1.6 terabytes per second of bandwidth. It's connected to 4 MI455 GPUs. And then there's also a set of 2 custom NIC cards in the front called Vulsi. Each one has 4 or 6 800 gigabit per second Pensando NICs. They're all tied together by a coherent XGMI or Infinity Fabric connectivity. Gives you 256 gigabytes per second between each GPU and the CPU bidirectional of bandwidth. The connections over to the NICs are done with UA link running at 128 gigabits per second, so it provides 256 gigabytes per second of bidirectional bandwidth to each one of those NICs. And then in the back, over those blind mate connections, I've done the same thing. What's going on here? Sorry. Bottom left. That's a design flaw. And then, yes, exactly. So, and then on the left, flow through this. Sorry. Perfect. Okay. And then the connectivity in the back gives you 3.6 terabytes per second bidirectional of bandwidth into the cable backplane. So very, very high bandwidth. All right, let's take a look now at the switch trays. We'll put the compute tray back in the rack, pull out a switch tray. The switch trays each have a pair of Tomahawk 6 Broadcom switches. They're 512 lane switches running at 200 gigabits per second per lane. There's integrated fabric management and controllers. There's a Ryzen CPU and a BMC on each one of these blades as well. And there's just a lot of bandwidth. This is a bandwidth monster. There's a total of 6 lanes between each of the switches and every one of the 72 GPUs in the compute pod, providing very high bandwidth. And again, blind mate connected into the cable cartridge. So you put this all together, and you end up with a pod that looks like this. You've got 18 compute trays, 72 total GPUs. Each one of them has 72 lanes of 200 gig Ethernet bandwidth out the back. They connect up to a set of 12 switches spread across 6 switch trays. Provides, again, 3.6 terabytes per second bidirectional per GPU, and it's shared memory across the entire fabric. So every GPU can directly load and store to its own memory, to its CPU's memory, or to the GPU or CPU memory of any of the other nodes in the machine. We also have the connectivity, direct connectivity of up to 3 800 gigabit per second NICs to each one of the GPUs, providing RDMA across the scale-out fabric, tying the entire cluster together up to hundreds of thousands of GPUs. Now, that's the hardware. Of course, hardware isn't any good without software, and in the same way that we're thinking about chip all the way up to data center scale in the hardware, we're thinking the same on the software. At the bottom level, we've got ROCm, which has been the foundational software over multiple generations of AMD GPUs. It provides management of compute workloads and node health and telemetry, et cetera. Then we have an AMD Fabric Manager that goes on top of that manages the entire scale-up network. Then we've got on each one of the switches, we've got a switch network operating system based on Sonic. It's got Fabric Manager agents that run directly on all of the switches. Above that, there's an AMD Rack Manager that provides telemetry and management, gives you unified visibility, single pane of glass across the entire fabric. And then there's a Cluster Manager that manages the entire multi-rack system at data center scale. It's got native Slurm, Kubernetes, model as a service integration, et cetera. And all of the AMD software is automatically instantiated when you bring up the system. One of the great things that the Fabric Manager can do is provide reliability inside and flexibility inside that pod. So you've got a collection of 18 nodes, and on a node granularity, you can carve out virtual pods. And within each virtual pod, you have full performance and reliability and security isolation. So no user in one pod can access any data outside that pod. If you have a failure, if you have a compute node that goes down, it only impacts your local pod. It doesn't impact the other pods, and you get performance isolation as well. The pods don't have to be contiguous. You can do anything you want on a node granularity. And meshing with that is a multi-layered resilience architecture that provides incredible protection against failures in the network. In a healthy system, you've got all 72 lanes for each GPU that are operational. If you have any transient errors, you have a bit error that happens on a transmission, it gets detected with CRCs, automatically retransmitted, nobody knows the difference. But sometimes you have hard failures. If you actually lose a link in this, then what will happen is the DMA traffic that's ongoing will reroute automatically and load balance over the remaining 71 links in the system. And so you'll end up with just about a 3% bandwidth impact. Loads and stores that are coming directly from the compute units need to get rehashed to get balancing, and that happens automatically as well by the Fabric Manager within about a second. Now, if you lose an entire switch, basically the same thing happens. You'll end up losing 1/12 of your bandwidth. All your DMA traffic will automatically load balance immediately with about an 8% bandwidth impact, and then the Fabric Manager will rebalance the compute unit traffic within about a second. And this can even be done at a switch tray. You could walk up to a running system, pull out an entire switch tray. Again, not a single packet is dropped. Everything gets delivered. Software does not get interrupted. If you have a compute failure, of course, you will have to roll back a software to the latest checkpoint. But any switch failures can be handled automatically with no interruption of software. Okay, so I will stop there. You've kind of got a quick overview of Helios. It provides this very powerful, very flexible, and very resilient rack scale GPU. I'm going to hand it over to Arvind now. He'll show you how you map workloads onto Helios for everything from a single rack all the way up to data center scale.
Thank you, Steve. Hello, everyone. In the keynote this morning, Lisa showed us where AI infrastructure is headed and the role that AMD is playing in driving towards that future. Steve walked us through the system that AMD is building to drive towards that future. In this section, I want to focus on the decision underneath every AI factory. How to match the right infrastructure to the right workloads, and why Helios is built for production at AI scale. Let's think about where we were in 2017. The transformer paper had just dropped, and the early models that followed were about 100 million parameters, and we called them large models. Today, agentic and reasoning systems operate at a trillion parameter scale. That demands a completely different class of systems. And the workloads that running on those systems have three fundamentally different profiles, each with a different dominant tax. So let's think about where we were in 2017. The transformer paper had just dropped, and the early models that followed were millions of parameters, and we call those large models. Today, agentic and reasoning systems operate at trillion parameter scale. That demands a completely different scale of systems. And the workloads running on those systems have three fundamentally different profiles, each with a different dominant tax. Training is long-running, massively parallel and synchronized. Thousands of accelerators work together to advance a job further, and the slowest path sets the pace for the entire system. For training, the dominant tax is coordination. So let's talk about inference. Inference is millions of independent requests, each with differing latencies, arriving continuously with users waiting in real time. The waits and the KV cache needs to be close to the compute. A few milliseconds of latency repeated at an AI factory scale can quickly add up cost. So for inference, the dominant taxes are data movement and tail latency. Agentic AI is completely different. An agent plans, retrieves context, calls models, calls tools, writes state, and executes. The workload is dynamic, bursty, and long-lived. For agentic AI, the dominant taxes are orchestration and state. Three different workloads, three different dominant taxes. These different dominant taxes demand different architectures. Force them all into the same infrastructure, and you could potentially end up winning a benchmark, but losing your business, leading to a higher cost, lower performance, and potentially a combination of both. So the principle for choosing the right infrastructure for your workloads is very simple. Start with your workload's dominant tax. Here's the framework that I use to evaluate any AI workload. Ask 4 questions. First, what is the time horizon? Are we talking about milliseconds, hours, or weeks? Second, where does the critical state live? Is it in waits and KV cache, gradients and optimizer state, or tools, databases, and sessions? Number 3, how fast and how often must your accelerators synchronize? And number 4, what in your system can fail independently? When the answer to these questions is a long-running job with synchronized progress across a massively parallel system, the architecture must scale out. Capacity and global coordination are on the critical path. When the answer is a latency-sensitive request that must stay close to compute, the architecture should scale up. Locality is on the critical path. When the answer is a nonlinear workflow that is bursty, spanning inference, tools, data, policy, and state, the architecture is hybrid. The intelligence plane and the orchestration plane have different needs, but they must work together as a single coordinated system. The architecture follows the critical path. Scale up for locality and utilization, and scale out for global capacity and coordination. And you combine both when the workflow needs both domains. Let's talk about the workload that clearly aligns with scale out, frontier model training. At an AI factory scale, the network essentially becomes part of the system. 3 things drive the architecture for scale out. First, synchronized progress. When thousands of GPUs advance together, the slowest path sets the pace. Second, resilience. Long-running jobs often encounter faults. The fabric must contain impact, it should create alternative paths and keep a component failure from becoming a job failure. And third, the data pipeline. The cluster must feed the accelerators continuously. Otherwise, expensive compute just waits. Collective libraries, NIC offload, congestion control, and telemetry all determine whether a cluster behaves like one coordinated unit or just a plain collection of parts. That is why Helios is scale-out ready. Up to 43 terabits per second of scale-out bandwidth through AMD Pensando, networking with programmable transport, congestion control, telemetry, load balancing, and the ability to operate the fabric as a system. The networking topology then follows the workload. A multi-plane, rail-optimized design adds parallel paths instead of tiers. It reduces hops, latency, power, and failure blast radius. Compute in an AI factory is only as valuable as the network's ability to deliver it. This is scale-out for the AI factory, when adding another rack creates more useful outcomes than just coordination cost. While scale-out is the destination for some of the workloads, the rack scale is the foundation for all of them. Today, the rack is the new unit of compute. It's not a server, it's not a chip. The rack is the new unit of compute. Frontier models today are too large to fit in an 8 GPU node. You are no longer thinking about single node performance. The question is, how do multiple GPUs across a rack behave together as one coordinated system? Helios brings together 72 GPUs, 31 terabytes of HBM4, and 260 terabits per second of scale-up bandwidth into one tightly coordinated domain. Why does that matter? Because the best network hop is the one that you do not take. Weights, KV cache, expert routing, and GPU to GPU communication all stay close to compute, improving latency, utilization, and useful output. Rack scale is also an operational boundary, a known envelope for performance, power, cooling, and failure behavior. Scale up first means taking a known good unit with known performance and failure behavior. You then scale out, meaning you replicate this with a known good unit across the entire AI factory, multiplying a consistently operating model. Let's move on to agentic AI. This completely changes the infrastructure equation again. An agent is not a single model call. It is a long-lived digital worker. It interprets, plans, calls tools, invokes models, and maintains state and executes. This creates two tightly connected planes. The intelligence plane, a dense CPU inference model, where Helios provides the memory, the locality, and the throughput to reason large models very effectively. The control and the action plane, CPU-rich infrastructure for gateways, scheduling, identity, tool execution, and persistent state. Highly concurrent, latency sensitive, and always on. The GPU generates the next token, and the CPU-centric system completes your next action. Scaling every step, sending every step to the GPU wastes premium acceleration on orchestration, and it creates an expensive system with no flexibility. The right architecture puts each phase of the engine that is built for it. AMD Instinct GPUs for dense model execution, AMD EPYC CPUs for orchestration and actions, and AMD Pensando NICs for high-performance observable connectivity. Agentic AI is the new systems architecture, and AMD has the CPU, the GPU, networking, and the software portfolio to build it as one integrated platform. So let's put it all together. So Helios is the production building block for the AI factory. It's scale-up optimized, model state, and high-density inference stay close to compute. It is scale-out ready. The same rack participates in distributed training and fleet-scale deployment through a fabric-aware multi-plane architecture. It is full-stack integrated. AMD Instinct, AMD EPYC, AMD Pensando, Brockam, fabric management, rack operations, all co-designed in one coherent package. And it is open. It is built on open standards with the observability, the reliability, and the ecosystem choice that customers need. One open, production-ready rack can take the right role across the entire AI workload spectrum. The infrastructure decisions that you all are going to make are strategic choices that have the potential to shape your organization's long-term success. To drive these infrastructure decisions, I would like you to leave this session with 3 key takeaways. Keep the critical path of the workload local. Distribute the workload only when it creates more useful outcomes. And put every phase of the workload on the engine that executes it best. To help accomplish this, AMD has built one rack that caters to every workload across the entire AI spectrum. That is AMD Helios. Thank you, and enjoy the rest of your conference.